Welcome. This video is going to look at the first part of section 4.1 in the Brown IB chemistry book. And in 4.1 they start looking at ionic bonding and just bonding in general. So the idea is that there's only 92 different kinds of atoms or elements, and yet we have millions of compounds around us. So how is that possible? It's possible because they bond or combine in lots of different ways. Ionic, covalent, metallic, a small number of atoms versus a large number of atoms, similar atoms bonding with each other versus different atoms bonding together. So there's all these different combinations, and a chemical combination of atoms that results in a stable structure is called a chemical bond. And atoms linked by chemical bonds have very different properties than their parent atoms, and kind of the key one they always use is sodium plus chlorine gives us this harmless table salt, but sodium metal by itself is a very reactive metal, even reactive in air. And chlorine is a poisonous gas when it's in its pure form. So how do we predict this bonding? It's all about the electrons or the electron configurations. So chemical reactions take place when some bonds break and other bonds form. And that's a key part of chemistry, is looking at how quickly those bonds break and how much energy it takes to both break the bonds and make the new bonds. So we're going to concentrate on ions or ionic bonds, and ions form by gaining or losing electrons. By definition, atoms are electrically neutral, so the number of protons has to equal the number of electrons. And during a chemical reaction, protons remain constant. If the protons change, then you have a big reaction called a nuclear reaction. But electrons can easily be transferred, meaning gained or lost. So, and the electrons generally that are being gained or lost are what we call the valence electrons. They're the ones found in the largest energy level of an atom, and they're the most likely to be transferred or shared. Now, we say most likely because with transition metals, they're filling either a d or an f orbital, and those d electrons can also get involved, but they're usually from the energy level before. Again, when atoms gain or lose electrons, the atom becomes electrically charged, and then we call it an ion. And the charge is going to depend upon the number of electrons gained or lost. And thanks to Ben Franklin choosing the symbols here, we go with positive being when you lose electrons and negative being when you gain electrons. So formation of ions, different elements tend to do different things. Noble gases tend to do nothing. They're the only elements that are already stable. So other elements are trying to become like noble gases. They're trying to acquire that similar electron configuration of S2P6 because for whatever reason, that is really stable. So remember, 8 is great, but 2 will do for elements 1 through 5 since they're only going to be filling energy level 1. So which is easier for metals and nonmetals? Well, it's all about size. Remember, metals tend to be larger atoms with the lower ionization energies. So it's going to take less energy to lose electrons. They're going to tend to form positive ions called cations. And metals tend to have 1, 2, or 3 valence electrons that they're going to tend to lose. Nonmetals, on the other hand, tend to be smaller. Remember, they're upper right, so they tend to be tighter. So since they're smaller, they're going to have higher ionization energy, greater electronegativity, and electron affinity. So they're going to tend to gain electrons, and they're going to form the negative ions called anions. Group 14 elements are kind of unique. Group 14 is what we usually think of as 4A. They have 4 valence electrons, so it's going to take about the same energy to gain or lose the 4 electrons. And they're kind of that middle size, or right in the middle of, the ionization energy. So either way, it's going to be a lot of energy to transfer 4 electrons. So what carbon and silicon tend to do is form covalent but not ionic bonds, whereas lead and tin, the 2 metals in that group, tend to behave like transition metals, and they often form a +2 ion, although they do also form a +4 ion. Transition metals, as I mentioned, are either filling a d or f orbital, which is not the outer energy level. So technically they have 2 valence electrons in the s of that outer orbital, but realistically they can also move electrons to or from the d or f orbital that they're in the middle of filling. It means they can lose 1 to 4 or even 5 electrons. Most commonly, definitely, is 1 to 3 electrons. How do you know? It depends on the reacting conditions. So you're not going to have to predict that. The oxidation number will be given to you by a Roman numeral after the name. But what it means is different ions form with distinct properties. Most recognizable color is very characteristic of the transition metals and what transition state it's in. The other group to mention are polyatomic ions. It's just what it sounds like. It's an ion made of several atoms. It forms when a group of nonmetals bond covalently, and then they either gain or lose an electron. So they need something to finish out the stability of the group. Most are anions, and most contain oxygen. So most of the polyatomic ions, in fact, if you look at the list below, all but one are what we call oxyanions. And you need to realize that IB doesn't supply the names and formulas in the data booklet, but if you look around, there's enough formulas in there of things that you probably can find these. But these are common ones that you should know: nitrate, hydroxide, hydrogen carbonate, carbonate, sulfate, phosphate, and ammonium. And we'll use them frequently throughout the year. So to wrap up, ionization is a process where electrons are transferred between atoms. So one atom loses electrons and another atom's gain these. More realistically, it's one atom is ripping the electrons off the larger atom, the smaller atom's ripping them off the larger. So it's usually a metal losing, while a nonmetal is gaining electrons. And then electrostatic force is the attraction between positive and negative things. So the resulting attraction between your positive and negative ions holds the ions together, and that's called the ionic bond, and it forms what we know as an ionic compound. And in the second part of 4.1, the next video, we'll look at the properties that leads to for ionic compounds. Overall, the compound has to be neutral because the electrons lost has to equal the electrons gained. They have to go somewhere, and again, think about it as the smaller one pulling the electrons off. You're not going to lose electrons just because. Something has to remove them. So an ionic formula reflects the simplest ratio of ions that can make the electrons lost equal to the electrons gained. So the easy way I think of doing that is you just crisscross oxidation numbers and then reduce or simplify the ratio. And remember, naming always involves listing the cation first, and then when you list the anion, you change the ending to IDE, such as oxygen becoming oxide or nitrogen becoming nitride, etc.